Episode 4 derived the sampling theorem, showing that a band-limited function can be exactly represented from periodic samples. Here we assume that we can measure the sample values at f at n, x equals n over 2b. We use this idea to analyze samples from this audio signal. Where did these samples come from, though? It's not actually possible to take exact samples from a physical distribution. If we could measure the signal exactly, we wouldn't have any need for computational imaging. But measuring the signal exactly at one point in space requires infinite resolution. In practice, the measurement system has some finite spatial response. If we assume the measurement system is a linear transformation, meaning that the sum of two signals produces the sum of their individual measurements, then we can use an impulse response to characterize it. Here, h sub n of x is the impulse response for the discrete measurement g sub n. So as with the sound system, we get discrete sample values at discrete points in time. Now, if you look at the sound system, of course, there's no need for a different impulse response for each of these signal values. We can assume that the same impulse response is used at all signal values, but it's shifted in time. So we have a shift invariant linear transformation system with this impulse response h of x minus n delta. Okay, so now what is h going to be? What is our measurement distribution going to look like? As we talked about last time, for focal plane arrays, for optical imaging systems, we often assume that we have rectangular pixels. So we integrate the signal over each of these square pixels in the focal plane array, and we can model h as the rect function over those pixels. In one dimension, that looks like something like this. We have a signal f of x, and then if we integrate the signal against the rect, for example, over this region, we get some value, and here we multiplied the rect by that value and represented the signal on the basis of the rects, and with a different value for each point in space. So this gives us kind of a chunky representation of the signal, and these are our signal values. G sub n are those rect values for each point in space. Okay, let's go back to talking about the sampling theorem, which now seems a little bit useless to us because we can't actually measure f at these particular points. So we could ask ourselves, is there any function that we could measure with infinite resolution? It turns out that yes, there is. Consider this function, g of x prime is equal to the convolution of f of x with this measurement impulse response that we just talked about. We can look at that function evaluated at a discrete value, x prime is equal to n delta, and it turns out that's what our measurement is. Our measurement is this function, g of x prime, evaluated at a specific value, x prime is equal to n delta. So we have evaluated this function with delta function sampling. And because we've evaluated with delta function sampling and we assume that our measurements are band limited, we can use the Whittaker-Shannon sampling theorem to represent the measurements in continuous form. So the sampling theorem turns out to be fantastically useful for us in terms of understanding what our measurement distribution looks like. But our challenge is to recover the object from the measurement distribution. So that's going to be the focus of a lot of the rest of our discussion throughout the course, but let's get to work on it now. Computational imaging. Episode 5, Wavelets. So we're still talking about computational optical imaging, and we're in chapter 2, and we're talking about section 2.5, Wavelets. Now, we just saw that we can take a function f of 0 and measure it with these Haar sampling functions, or the rect functions, but we're going to start to call those rect functions the Haar wavelet, the square function between minus 0.5 and 0.5. Now, it could be that we look at this system, we say, well, this plot is too coarse. I would like to know more detail about this function. So say, no problem. We'll make our rects half as wide. We'll use a finer rect to sample. And you see that if we do sample with a finer rect, we get a better representation of the signal. So we can continue this process, say, let's use a finer rect than that and a finer rect than that. And eventually you see that the rect function, these little square functions, do represent a pretty accurate representation of the function if we sample fine enough. So we have the idea that we can represent functions by making our sampling finer and finer. We can formalize this process mathematically. The representation of the signal using the the first order function. We call this first order function beta 0. Beta 0 is the Haar wavelet. The rect function is the zeroth order function in the B-spline functions, so that we can make higher order B-splines or different basis functions by convolving the rect function with itself. But here we're interested in just the B0 function, and we've represented the function as a sum of projections onto these B0 functions, which is very similar to what we did with the Fourier series. But here we've represented the function on these rect functions, and we call the function represented on this as the function projected onto the space of V sub 0. V sub 0 is a vector space of functions with the basis of these rect functions. And so any function that is represented on this basis, if we add those functions together, we're still in that vector space. And each of the components is found by integrating over the region of the corresponding rect to find the projection onto that space. Now, again, if we want to go to finer representations, we just make our basis function finer and finer. And so we have a multi-scale representation that we could phi 0 would be the rect function of width 1. If we go to a rect function of width 0.5, we have phi minus 1. Rect function of 1/4, we have phi minus 2, and so on to finer and finer scales. We can define these basis functions for each scale just by rescaling the basis function for the 0th scale. Each one of these scales represents its own vector space with the property that because I could just add this function plus this function shifted, I can get the basis function for the 0th from the basis function for the minus 1 level of functions, that each higher level function is a subspace of the vector space represented by the next level down in functions as we go to finer and finer. So any function that could be represented on this basis can be represented on this basis, and then any function that can be represented on this basis could be represented on this basis. Now, we might want to figure out how we could have a set of two different vector spaces that add together to represent the functions on a lower level basis. So we can define a wavelet basis, a wavelet space W sub j, such that the sum of the vector space V sub j and the vector space W sub j represents all functions on the vector space V sub j minus 1. This we can use as basis functions are these wavelet functions. So one thing that you'll notice is that if I take the basis function on the 0th level plus the wavelet function on the 0th level, I can represent the basis function on the minus 1 level. If I add this function to this function, then this part would cancel due to this, and so I would have just this function. If I subtract those two, then I would get the basis function shifted by 1 on the lower level basis. So I can create, by these two higher level, the basis function and the wavelet function on the 0th level, I can create the basis function on the next level down. One thing you'll note that's interesting is that the basis level, the wavelet spaces on successive levels are orthogonal, so that if I integrate this wavelet function projected onto this wavelet function, it integrates over just this region and gives 0. So where the basis functions on successive levels are not orthogonal, the wavelet functions are orthogonal. What this means is that I can represent a function by its projection onto the basis onto the wavelet functions. If I sum over all scales and all positions of the function, that I have a way to represent the function f of x for any square integrable function on the sum over all the basis states, or over all the wavelet states. So this gives us an alternative to the Fourier series and the Shannon expansion that we had for band-limited functions and functions with limited support. Here, any square integrable function can be represented in discrete form on the wavelet basis. Oftentimes, we may want to take the function, rather than going infinitely positive scale on the wavelet basis, we may start with the function on some scale with the 0th order function, for example, our square wave function, that we started our discussion with today, and just refine it to higher order levels. But now, rather than having to, like we did back on a previous slide, record information at finer and finer levels, we only have to know the wavelet expansions at the finer levels in order to fully represent the function, because then we can recover the function on that scale by combining its basis function and its wavelet function representation. We can expand this representation into 2 dimensions using a rectangular products of wavelet functions in x and y, where we use the products of the basis functions on each scale in x and y, and then we define these the horizontal and diagonal wavelet functions as products of the basis functions and the wavelet functions with products in x and y. This approach is equivalent to taking an image and saying that we would add the images, for the low-level basis functions, we add the images in a block, we add the pixels in a block all together, and then we take differences of pixels to get the wavelet projections onto the diagonal and horizontal and vertical wavelet basis. If we implement this on a particular function using the NumPy code provided, you see I take a given image, the averages are the sum of pixels in these blocks, the 2x2 blocks. The horizontal differences emphasize horizontal features in the image. The vertical differences emphasize vertical features in the images, and the diagonal differences are shown here. One thing you'll notice is that images tend to be sparse on the wavelet basis. So if we have the average of the image is not sparse, when we look at these differences of pixels in local spaces, we get the image that's extremely sparse on this basis, and this is used, as we'll discuss in chapter 7, for image compression. Now, here we had a 512 by 512 image. Each one of these wavelet decompositions is 256 by 256. So we have the same amount of data. We still have 512 by 512 total data size, but we've broken it up into these 4 256 by 256 images. We could take the averages and take the wavelet transform of that again and turn that into something where now we have 4 128 by 128 images. And you see the average image looks a lot like the underlying image, so if you want to give somebody just a general idea of the image, you can give them just the averages at some scale, and then as you want more information, you fill in with the wavelet information from higher scales, which, because it's sparse, will tend to be easy to transmit. So our point for this today is just to show a different representation, or a different discrete representation of a signal. We started again with the Fourier series representation, the Shannon representation. Now we see that we can represent arbitrary signals as being represented on a wavelet basis. We've shown this today just with the Haar wavelet basis. We talked earlier today about how we cannot directly measure discrete samples of an image. The wavelet projections are in principle measurable, right? We could use the wavelets as the impulse response functions. So these are measurable features of a function that, if measured at finer and finer scales, could completely represent the function. So what we've seen is that with several examples, for an arbitrary distribution f of x, we can represent it as a discrete series on some basis, or a discrete sum on some basis of basis coefficients. What we're going to do moving forward is assume that we could use arbitrary representations of the underlying distribution of this signal. One of the things that we talked about, of course, is we could represent the signal on the Shannon basis with these samples. And at the beginning of today's discussion, I said that this is kind of useless because we can't directly measure those samples, f of n over 2b. But maybe we don't care, because we still represent the signal in this way, and we can analyze its representation through our measurement process. So the measurement process, again, is going to have some impulse response, and we get some discrete measurements. If we assume the signal is represented on some discrete basis, which could be the Shannon basis or the wavelet basis, then we can represent the measurement process as a matrix vector product, where the coefficients in the matrix are represented by the projection of the basis function for the underlying function onto the impulse response of the measurements. This allows us then to get to the main point that's going to be our underlying key problem in computational imaging, that our measurements are typically a linear projection of the object distribution. So estimation of the object features represented discretely by this vector f from the measurement represented discretely by the vector g is the key problem that we need to dig into to solve computational imaging. And we're going to get into that in our next